All right, everyone, welcome. Today, we're kicking off our journey into something that's, well, pretty much everywhere, but often goes unnoticed: advanced electric drives. We're going to really get into the nuts and bolts of how they control speed and torque. And trust me, it's the secret sauce behind a ton of the tech you use every day. So, let's get started.
So you might be thinking, electric drives, why is this a big deal? Well, think of them as the unsung heroes of our modern world. I mean, they're the workhorses behind the scenes. The elevators you ride, those cool robotic arms in car factories, even the pumps that keep everything flowing. Yep, that's all them. They are quite literally everywhere, and modern life just wouldn't work without them. And here's the thing, their role is becoming even more critical. I mean, look at the huge shift we're seeing towards green energy. Electric drives are right at the center of it all. We're talking about electric vehicles, those massive wind turbines you see, the efficiency of those entire systems, the thing that makes them work so well. It all boils down to how precisely that electric drive is controlled.
Okay, so whether we're talking about an elevator or a wind turbine, what's the one thing we're always trying to achieve as engineers? What's the core objective? It really comes down to this one really elegant concept: maximum torque per ampere. In plain English, we want the most rotational force possible, the most twisting power, for every single amp of current we pump into it. It's all about getting the most bang for your buck, electrically speaking.
All right, so we've established that these drives are super important, and the goal is maximum efficiency. Sounds straightforward, right? Well, actually, making that happen in the real world throws a pretty big challenge at us. Let's dig into what that fundamental control challenge really is.
The whole game is about control. See, a really high-performance drive needs to react, like, instantly to any command you give it. But how do we know if it's actually doing that? We can't just guess, right? We have to measure it. And that's where tools like this oscilloscope come in. It lets us literally see the electrical signals, the voltage, the current, and gives us a window into how fast and how accurately that drive is responding.
And this graph, this is a perfect picture of what we're talking about when we say fast response. Take a look. The horizontal line there, that's time. The vertical is torque. Now, see that blue line? That's what we're asking the motor to do. It's the command. See how it just jumps up? Now look at the orange line. That's what the motor is actually doing. It's tracking that command almost perfectly, with virtually no delay. That, right there, is the holy grail of drive control.
So let's be really clear about this. This rapid, precise torque control, it isn't just some optional extra. It's not a nice to have. For any system that you'd consider high performance, we're talking precision robotics, high-speed rail, you name it, this is an absolute non-negotiable requirement. It's the bare minimum. It's the price of admission to even be in the game.
Okay, so we've laid out the problem. The big question is, how do we solve it? Well, modern engineering attacks this with two main tools in the toolbox: AC drives and the power of simulation.
You know, for a really long time, DC motors were the way to go. The control was pretty simple, which was great. But they had this big downside: mechanical brushes. These things would wear out, create dust, and just needed a lot of maintenance. That's why you've seen this massive industry shift over to AC drives. Now, the control for AC is way more complex, for sure, but the game changer has been fast digital signal processors. These little powerhouses can handle all that complexity, which lets us have brushless designs. And what does that get us? Way higher efficiency and just rock-solid reliability.
And a huge piece of how we wrangle all that complexity is simulation. Think about it. Before we spend a dime on actual hardware, before we even touch a screwdriver, we build the entire thing virtually. Simulation is absolutely essential today. It's like a digital sandbox where we can understand how the system will behave, develop all our fancy control algorithms, and basically test the heck out of it, all in software. It saves so much time and money.
Now, the term AC drive covers a lot of ground. It's a big family of motors. For our purposes, we're going to zero in on three of the most important types. First, the induction motor. It's the absolute workhorse of the industry. Then you've got the permanent magnet AC motor, which is all about high performance. And finally, the switched reluctance motor, which is just tough and robust. We're going to get into the nitty-gritty of each one, looking at their unique physics and how we control them.
Look, to really understand this stuff, we can't just stay in the world of theory and equations forever. We need to ground it in something real. So we're going to use a concrete example, a standard model that will be our baseline for all our analysis and our simulations. This is super important because it makes sure that we're all on the same page, all comparing apples to apples.
And here it is. This is going to be our test subject. It's a 1.5 megawatt induction machine.
I mean, this is a serious piece of industrial hardware. This beast is going to be the foundation for all the simulation work we do in this course, so you are going to get to know it very, very well.
So, let's look at the spec sheet, the vital stats for our machine. On the left, you've got the general stuff. Power, voltage, the basics. But for what we're doing, for control design, the real magic is in the numbers on the right. Those are the per-phase equivalent circuit parameters. These values are what define the motor's electrical DNA, its personality, if you will. You'll want to pay really close attention to values like the stator and rotor resistance. That's RS and RR. These are the numbers that we're going to plug into our simulations to make them accurately reflect the real world.
All right, so to wrap this up, I want to leave you with a little thought experiment. We just saw all those precise parameters for our motor, right? Things like the rotor resistance, RR. So here's my question for you. What do you think would happen if that one value changed by just 10%? Maybe the motor heats up or it's a slightly different model. How would that tiny change impact the motor's ability to give us that beautiful instantaneous torque response we saw in that graph? It sounds like a small thing, but believe me, in the world of high-performance drives, a small change like that can change absolutely everything. Something to think about for next time.
All right, welcome everyone. Today we are diving deep into the science that makes an electric car leap off the line and a factory robot move with, well, superhuman precision. We're talking about advanced electric drives. This is really the brains and the muscle behind all the high-performance systems that power our modern world. So let's get right into it. Just think about your day so far. Did you ride in an elevator? Maybe use a tool that was built in a factory? Did you benefit from a stable power grid? If you did any of those things, chances are you've already relied on advanced electric drives. They are the hidden engine in pretty much everything, from the robots that assemble our cars to the wind turbines that power our homes. Understanding this stuff isn't just about passing the class. It's about putting yourself on the cutting edge of engineering. So here's our roadmap for today. We're going to start with the why, the big picture applications. Then we'll zero in on the fundamental control problem, the real nut we have to crack. We'll talk about the technology shift to AC drives, introduce the standard motor we'll be analyzing all semester, and then finally, we'll look at the really exciting, real-world problems you'll be able to solve with this knowledge. Okay, so first things first, before we get lost in all the complex equations and the control schemes, it is absolutely essential to understand why this subject is so incredibly relevant right now. I mean, the applications are literally everywhere. Think about the smooth, precise, fluid motion of a robotic arm. Yep, that's advanced control. Or think about squeezing every last watt of efficiency out of some giant industrial pump. That's advanced control too. And maybe most critically, the entire green energy revolution, from these massive wind turbines that have to adjust to gusty winds, to that instant torque you feel in an EV, it is all built on the foundation of perfectly controlled electric drives. So this brings us right to the fundamental engineering problem, the real heart of our course. It all, and I mean all of it, boils down to achieving perfect, instantaneous control over a motor's speed and torque, especially when conditions change on a dime. Just think about this for a second. Imagine that robotic arm in a factory. It picks up a part that's suddenly twice as heavy as the last one. Now, without a really sophisticated control system, what's going to happen? The arm would slow down, right? It would bog down, and that could ruin the entire production process. The challenge, the real engineering magic, is to respond instantly to that change in. Okay, let's break this graph down, because this visualizes the single most important concept in this entire field. Up top, you see the load torque. We'll call it T-load, and you can see it suddenly jumps up. That's our robot picking up the heavier part. Now look below it. To keep the speed, that's omega m, perfectly flat, perfectly constant, the motor's own electromagnetic torque, or TEM, has to perfectly and instantly match that jump. You see that? It's a perfect mirror image. That instantaneous response, that is the holy grail of drive control. That's what we're all chasing. Now, historically, if you wanted precise control, DC motors were the go-to. But there's been a major technological shift, and it's the reason this course focuses pretty much exclusively on modern AC motor drives. So back in the day, DC motors were just easier to control. Their torque was directly proportional to current, a nice, simple relationship. AC motors, on the other hand, are way more complex. But the game totally changed with the arrival of cheap, powerful microprocessors. These little chips can run incredibly sophisticated algorithms in real time, which basically gives us the brains we need to tame the complexity of AC motors. And that unlocked their superior robustness and efficiency, letting them completely take over modern high-performance applications. Okay, so to analyze these complex AC drive systems effectively, we need a consistent framework. We need a common ground. So throughout this course, we're going to use a standardized model and some powerful simulation software to make sure we're all speaking the same language. And let me be really clear about this. A simulation-based study is absolutely essential for this field. I cannot overstate that. These systems are just way too complex to analyze with a pen and paper alone. We're going to be using software like MATLAB and Simulink to build our models, test our controllers, and see how they perform, all before a single piece of hardware is ever built. It's how modern engineering is done. And to make sure we have that consistency across all our analyses and simulations, we're going to use a single, standardized motor as our reference. As the textbook says, we are going to select a 1.5 megawatt induction machine as our official test machine for this whole course. Now, what I find really fascinating here is how we can take a real, physical piece of heavy machinery and just boil it down to these 6 key numbers. This is our digital twin. We've got its power, its voltage, its frequency. We even have its inertia, which is just a measure of how hard it is to get spinning. Every single simulation we run, every controller we design this semester, it's all going to start with this exact data set. This is our ground truth. So you might be asking, why are we so focused on this one test motor? Well, it's because mastering this model isn't just some academic exercise. It's the key. It's what unlocks your ability to go out and tackle some of the biggest engineering challenges facing the world today. And this is where the theory gets real. This is where it gets fun. This knowledge leads directly to designing control systems that help a wind turbine squeeze maximum power from every single gust of wind. It's what's inside the next generation of hyper-efficient EV traction drives. We'll even get to deconstruct legendary systems like the Toyota Prius's hybrid synergy drive to see exactly how these principles work out in the wild. So the crucial point is this: the theory, the simulation, and the analysis that we're about to get into, they are not just abstract concepts. They are the professional tools that are going to empower you to design, to build, and to control the sophisticated electromechanical systems of the future. So I'll leave you with this final thought. As we go through this course, don't just think about the problems in the textbook. I want you to think bigger. How are you going to take these principles of precise torque and speed control to innovate in robotics, to advance renewable energy, or to completely redefine transportation? The possibilities, and I mean this, they're endless.
All right, welcome. Today we are jumping headfirst into the world of advanced electric drives. We're going to break down the analysis, the control, and the modeling that honestly powers just about every single part of our modern world.
So here's our game plan. We'll kick things off with why you should even care about electric drives. Then we'll nail down the single most important control objective. After that, we'll walk through our approach and the tools we'll be using. And we'll wrap up by applying all this knowledge to some really cool real-world examples. Let's get right to it.
Okay, first things first. Why does any of this matter? Well, for you as engineers, getting a handle on electric drives is absolutely critical because, to put it simply, they are the invisible force making almost everything around us work.
I mean, these drives are the unseen workhorses all around us. Just think about the elevators and skyscrapers. They need to run with perfect, smooth reliability day in and day out. Or what about industrial robots? The only reason they can assemble cars and smartphones with such incredible speed and precision is because of the electric drives inside.
And you know, this field gets even more critical when you start looking at green technology. The constant push for more efficiency. I'm talking about getting the absolute maximum torque for every ampere of current. That's what makes things like variable speed wind turbines and of course the electric vehicles that are totally changing transportation even possible.
So now that we see why these drives are so important, let's get down to the nitty-gritty. What is the fundamental engineering challenge? What are we actually trying to control here?
The name of the game, the one core objective, is instantaneous torque control. Take a look at this graph. See how the load torque suddenly jumps up? That could be an elevator starting to go up. For the speed to stay perfectly constant, the motor's internal electromagnetic torque has to jump up at the exact same instant to match it perfectly. Nailing that response, that's our central challenge.
Now, achieving this kind of control has really evolved. Way back when, DC motors were the easy solution because, frankly, they were just simpler to control. But the real game changer for AC motors was the arrival of powerful, cheap microprocessors. They give us the horsepower for the complex, super-fast signal processing we need to get incredible performance out of AC machines. And for that reason, AC drives are now the industry standard, and they are going to be our entire focus.
So, with systems this complex, how in the world are we going to tackle them? Let's demystify our approach and break it all down into a clear, totally manageable framework.
Our entire approach really rests on three main pillars. First, we're going to focus on the physical intuition. What is physically happening inside the machine, not just getting lost in the math. Second, we're going to use a really powerful tool called space vectors. They let us visualize these complex, rotating magnetic fields as a single manageable point, which is awesome. And third, we'll bring it all together by integrating the power electronics, the PPUs, with feedback control so we can see the whole system in action.
Okay, to keep our work consistent and to make sure we can compare apples to apples, we're going to rely on a standardized toolkit for both our software and our hardware.
Our go-to software is going to be the industry-standard MATLAB and Simulink. It's just perfect for modeling and analyzing these drive systems. It lets you learn really fast and makes developing real-time hardware controllers so much simpler.
And on the hardware side, to keep everything consistent across all of our examples and simulations, we are going to use one single standardized test machine, this 1.5 megawatt induction motor.
And here are the nameplate specs for that test machine. You can see its power rating, voltage, frequency, and some other really key parameters like the number of poles and its moment of inertia. These values right here are going to be the foundation for every single model we build.
So how do we go from a big, physical machine to a model we can actually work with? We use this, the per-phase equivalent circuit. This little diagram is amazing. It translates the machine's physical properties into electrical components, resistances and reactances for the stator and the rotor. This circuit is literally the heart of our simulations. It's what allows us to accurately predict how the machine is going to behave.
Okay, so we've got our foundation, we've got our toolkit. What's the payoff? What can we actually do with all this? Let's check out how this knowledge applies to some pretty exciting real-world case studies.
For our first case study, we're going to dive right into renewable energy. We'll analyze the adaptive torque control strategies that are used in these massive variable speed wind turbines. You're going to learn how to describe and explain the core control logic that lets these incredible machines extract the maximum possible power from the wind.
Next up, we're shifting gears and moving to transportation. We're going to investigate all the different motor technologies used for the traction drives in hybrid and electric vehicles. You'll be able to do critical analysis, figure out what happens if certain materials aren't available, and really evaluate the pros and cons of different designs.
And for our final case study, we're going to do a deep dive and basically dissect a complete, commercially successful system, the hybrid synergy drive from a 2010 Toyota Prius. We'll identify all the key components, the power control unit, the electronically controlled CVT, and investigate the exact type of motor that's at the heart of this iconic hybrid.
This roadmap lays out exactly how we're going to build your expertise. We're going to start by mastering induction motor drives. Then we'll move on to the inverter synthesis that controls them. And finally, we'll apply all of that to even more advanced machines like PM servos and switched reluctance motors. It's a logical progression, step by step.
And of course, you're not going on this journey alone. We'll be using some excellent resources to support you. Our main textbook is Advanced Electric Drives by Ned Mohan, and we'll supplement that with online materials from the publisher, Wiley, and of course, from MathWorks for all of our Simulink work.
So remember this: instantaneous torque control, efficient power conversion, intelligent feedback. These aren't just abstract ideas. They're the fundamental tools that you are going to use to engineer the future of motion, whether it's in green energy or electric vehicles. So the real question is, are you ready to get started?